In the last lecture, we indicated that ionization chamber, is the other very important component of a mass spectrometer. Because, like we said, mass spec, can only analyze ions. So it's completely essential, for you to have an ionization platform, as a component, for the mass spectrometer. There are many different types of ionization methods out there that are mainly designed, for ionization of different types of chemical entities, as well as, different types of molecules, as well as atoms as well. Now, some of the ionization methods, are fairly energetic, it's what you call, harsh ionization methods. And there are others, that are fairly, soft ionization methods as well. This means, for very soft ionization methods, you do not fragment, your chemical entity, whereas, for very harsh, ionization methods, you tend, to fragment, your chemical entity. Now, that can be a disadvantage as well as an advantage, as you're gonna see, in a couple of slides. So, there are all these different types of ionization methods, again, that can be classified as either harsh, meaning they're very, very energetic. They result into fragmentation, of your analyte in most cases. And there are others, that are fairly soft. And of course, the softness, can be can be relative as well. Some are moderately soft, others are very, very soft, meaning they do not cause much fragmentation. So let us start, with the very most common, ionization method out there that you're gonna see it prevalently used, and that is what you refer to as electron impact. An electron impact, just refers to, you've got a filament, and of course, a filament, is gonna be producing electrons, and then you've got, your sample, going through, the filament. Of course, you've got, down here an electrode, which would be positively charged, so that you can pull, the electrons that are being generated by the filament, and then you get, your analyte, being impinged, by those electrons that are fairly energetic. And of course, the level of their energies is dependent, on the electrode here. If the electrode is pulling very strongly, maybe connected to, say plus 1000 V, then it's gonna be pulling the electrons very, very strongly, meaning they're gonna be, going at a very high energy. They're gonna have a lot of kinetic energy, and so it's gonna impinge on your analyte, to generate, an ion, So that's ionization. That's electron ionization or electron impact, ionization. So electron impact ionization, as you can see, is very, very energetic. Typically, these electrons, are moving at about 70 electron volts, when you apply a fairly high positive charge, electrode, Again, you can see the importance really of electrodes, that have introduced you guys to the lab in electrochemistry, but in this case, of course, being used in the mobilization of electrons as well as mobilization, of the ions. So electron impact is a fairly harsh, ionization method out there, and it causes a lot of fragmentation. Now, the other type of ionization method is called chemical ionization, and I'm going to show you in a couple of slides. It is very, very similar, to the electron impact. The only difference is, you introduce into the filament or into the electron impact ionization chamber some buffering gas, so that, the analyte does not get, the extreme energy being impinged, coming from the electrons. So you introduce, some reagent gas, and the reagent gas, gets ionized, and the charge is transferred softly to the analyte. So you can see it's almost a derivatization method. It's almost a chemical derivatization method where you derivatize the reagent gas using electron impact, and then the charge in the reagent gas, is transferred to the analyte using different types of mechanisms that I'm gonna talk about, either protonation, deprotonation, and so on, even cationization sometimes. So this chemical ionization really is a little bit, softer, compared, to the electron impact. And you're gonna see EI as well as CI are very common techniques, with the GCMS. So meaning in most cases the inlet, the sample is coming, from a gas chromatograph, and then you're having ionization, the EI and the CI, and then the mass spec after that. So the upstream in most cases of EI and CI is actually a GC. Now, there are other types of ionization methods called desorption methods, and these ones are often very common when you're working often, with LC as well, liquid chromatography. Is the upstream, technique in most cases, not in all cases. Some of them, are standalone techniques, meaning you do not need separation upstream. So some of the desorption methods, include things like field ionization. It's a very, very soft technique. You've got field desorption. Again, it's a very, very soft technique, and it's gonna see the ionization approach really is based on using electrodes or high voltage electrodes. You've got a very, very soft technique, maybe the softest of all, called electrospray ionization. Is the softest analytical ionization method out there, very common, for analysis of proteins. You're also gonna see you've got the MALDI, matrix assisted laser desorption ionization. Again, it's a very soft ionization method, maybe not as soft as ESI, but relatively soft. In fact, if I may mention, that's what I did, for my PhD. My focus was actually mass spectroscopy, the MALDI specifically. And then you've got others, like the plasma desorption. There's a fast atom bombardment. There's what you refer to as secondary ion mass spectrometer. Again, secondary ionization. And lastly, you've got this method called, the thermospray ionization. Now, all these are relatively, soft ionization techniques. So be able, to classify all these different types of ionization techniques based on whether they are soft or harsh, and also, be able to explain, how they actually work. And a couple of slides that follow actually are gonna explain, how they work. Now remember also something like the ICP, which is a thermal, based type of ionization. It's also an ionization technique. I think you guys already know that, that the ICP, which is a plasma, which is a very high temperature plasma, can also be used as an ionization method, right? I think that one is fairly obvious, so long as, it can be used as an ionization method. And I think I've already explained to you guys before, how the plasma, the ICP plasma torch actually works, so you just need to refer to that. So remember that the ICP can be used, as an atom ionization, method. So it's sort of it's used, for atomic, really, spectroscopy in that case. Now, when you're using ICP for ionization method, take a look at this, the difference in terms of the data profile between an ICP optical emission spectrometer that you guys used in the lab, compared, to an ICP mass spec. So you can see in this case, the ICP OES tend to be more prone, to what you call spectral, interferences. You can see it's a very, very busy, kind of spectra. whereas the ICP mass spec, you can see, is a fairly clean spectrum. So remember, the ICP mass spec, can give you information about the oxidation, state, of your atoms. Very, very important. Remember that. All right, it can give you the oxidation state, of your atoms, because remember, you're looking for the mass to charge. Meaning, if at all I've got, say, iron 2 plus, the mass of iron, the atomic mass of iron is known, and the charge of the ion is gonna be 2 plus, so when you take a ratio of that, that's what's gonna be, in your x-axis. On the other hand, when you've got ion 3 plus, yes, the mass is the same, but the charge is different. It's going to be 3 plus. So again, in the x-axis, you're going to see there's a differential mass to charge, of ion 2 plus compared to the ion 3 plus, meaning you can actually differentiate between them. If I look at this, you've got selenium, you can differentiate, different types of selenium as well. So again, very important, for speciation. Speciation, again, refers to when you're looking at in what oxidation state is my analyte. Is it high oxidation state, low oxidation state, and so on. And oxidation state, very, very important, especially, in environmental toxicology, because it determines, the toxicity, of your analyte. So very, very quickly, if I may classify some of these, ionization methods, a few of them, based on the molecular weight, of the nature of the analyte, that they are able to ionize. So take note of this. And also, the ionization that you use is also dependent, on the type of the polarity, or the volatility, of the analyte, that you want to ionize. For example, GC, maybe I can call it EI, because the most common, sort of type of ionization method with the GC, and to some extent, the CI as well. As I said in the previous slide, those are the two techniques, ionization techniques used to the GC. So those ones, they are mainly used to analyze non-polar as well as fairly low molecular weight, type of analytes. And as you can tell, that combination of non-polar and low molecular weight types of analytes are what you call volatile compounds. All right? Meaning they are very good, to analyze what you refer as volatile organic compounds, or what you call the VOCs, So you can see, the EI, the CI are fairly good, for analysis of fairly small molecules. On the other hand, atmospheric pressure chemical ionization, okay, which is actually a little bit different, from this CI. This CI is referring to where you actually use electron impact that is already inside the vacuum, all right? Whereas atmospheric pressure, chemical ionization, as you can tell, atmospheric pressure means, this ionization is not quite in a vacuum, okay? And so it's a different, actually often you got the LC, going to the atmospheric pressure chemical ionization, whereas these are the CIs, for the GC, so they are a bit different. Now, based on that, you can tell anyway, that the APCI is typically used, for moderately higher molecular weight compounds and relatively, non-polar, types of compounds. Look at thermospray ionization. Is typically used, for moderately higher, molecular weight compounds, and typically, for moderate, type of polar, compounds. Fast atom bombardment, again, you can see sort of where it ranges in its scale. But my focus actually is for you to see the ESI, which is maybe now the gold standard, for analysis of polar compounds out there. So it's very, very good for analysis of very large molecules or even very small molecules, so long as, they are fairly polar. So very, very important, for things like urine analysis, small drugs analysis, analysis of proteins as well, and so on. So ESI, you're going to find, is becoming a very predominant ionization technique, because of its wide, applicability as far as analysis of biomolecules, are concerned. Because, of course, biomolecules can be big molecules, and also they can be fairly small molecules, but in general, they are fairly polar as well. So let me very, very quickly, talk about how each of these techniques, in far as ionization methods work, in terms of the mechanisms, of how it works. And again, mechanisms are key, because that's the only way you can apply. If you understand how things work, then you can use that knowledge, and translate it or apply it, to a different type of, application, which is the essence, really, of higher education, to be able to translate what you learn, into, solving societal problems using that knowledge. So mechanisms are key, in my view. Now, electron impact, as I've mentioned before, you've got, a power supply, you've got a filament essentially. The filament is generating, electrons. And then those electrons are being pulled, by an electrode here. I'm just going to call it, an anode. And the anode, you can see, is positively charged. Depending on the voltage that you apply on the anode, that's going to determine, the kinetic energy by which these electrons are flying, across, that channel. And so you can see the neutron molecules, pass through, these very harsh environment, where electrons, are moving at very energetic, very high speed. And due to that collision causes ionization, and whatever is coming out, becomes an ion. As I've said before, it's very, very harsh. In general, the electrons have got very high energies, and for that reason, you get the analyte, being ionized. Now, the analyte that is being ionized, because of this very volatile environment, a lot of collisions, typically the ion that you actually get is still of very high kinetic energy as well. And because of that, the kinetic energy that is within this ion that is moving at a very, very high speed also causes, much further fragmentation. And so you're going to see, this is what you call the molecular ion. If at all I've got a neutron molecule, and then I just dislodge one electron, I typically get something that looks like that. People call it a molecular ion, okay, because I've only dislodged only one electron. But then, these molecular ion typically have got a lot of kinetic energies because of the volatile environment, that I talked about, that comprises, of electrons, that are very energetic. And so because of that, it tends to fragment, to release some of that energy. And so you get often, a lot of fragmentation, occurring. In fact, in some cases, these ion fragments completely, such that you never see it actually, in your spectra. So typically you would have something like that, that the signal or the intensity. And then, of course, you would have, the different types of fragments. And typically the molecular ion, of course, if at all it exists, is going to be the highest, molecular weight mass to charge ion. But again, as I say, depending on the type of molecules you're analyzing, sometimes you never actually get to see the molecular ion because it tends to fragment, completely. I'll give you an example. Typically, if at all you've got a hydrocarbon out there, it's very rare, to see the molecular ion. But if at all you've got, an aromatic type of compound out there, it's more common, to see the molecular ion, because the molecular ion tends to be stable, if at all you've got a conjugated environment, such as an aromatic compound. Again, there's a lot of chemistry actually involved in this, which I wouldn't get into. It can be fairly complicated. The gas phase chemistry can be fairly complicated, which is what we are dealing with. And of course, we don't have a lot of time, for that. But again, the emphasis is a harsh method of ionization, and it causes a lot of fragmentation, for small molecules, often that are volatile, which is the most common application of the EI, because it's the ionization method used with the GC, and GC typically is used to analyze volatile or semi-volatile organic compounds. So advantages of this technique, it is fairly sensitive, EI, very, very sensitive. Now, it causes a lot of fragmentation. That is a disadvantage, like as I said, the molecular ion can disappear, but it's also an advantage in the sense, from the fragmentation pattern, I would be able to piece together what type of a molecule, it was. So it's fairly good, for structural elucidation. So it's a very good technique for structural elucidation, because I can try to piece, the fragments, that came, from the ionization of the neutral molecule. So it's a very good technique, essentially, for qualitative analysis, as I've been trying to say. If at all I don't know what it is, I can fragment it, put the puzzles together, and from the puzzle, I can try to determine what I was starting with. A few disadvantages also, you need the sample again to be volatile. Typically, it's used for volatile samples, meaning you're fairly limited. If at all you've got a fairly polar compound, it's not volatile, then basically you cannot use the EI. So the other type of technique, that is a little softer compared to the EI, is a chemical ionization. As I said before, it's exactly similar to the EI in terms of the type of chamber that is used. It's a filament. You've got an anode that is pulling, those electrons. And then you've got the neutral species, going through that high volatile environment containing the electrons. The only difference is that you add into that environment what you refer to as the reagent gas. And typically you add the reagent gas, in fairly high volume, all right? Meaning, that the electrons' probability of heating the reagent gas are a lot higher, than for them to heat the neutral molecules. Now, the reagent gas then, would get ionized, because of its impingement, onto these very high energetic electrons. And when the reagent gas get ionized, it would transfer that charge softly, to the analyte, so that is, and that's why you're calling it, it's almost like a chemical derivatization method. Let me just give you an example, because methane, is a very common type of reagent gas that is used, with chemical ionization. So you get the methane, and the methane, would get ionized, by the energetic beam of electrons, and to be ionized, into the molecular ion, of methane. But again, the molecular ion of methane, would react with something like another neutral methane gas, to give you this type of a species, that is charged. Now, that species, can now react, with the analyte and transfer a proton. You can see it's protonation, depending on the nature, of course, of the analyte. If I call the analyte, has got, an amide group, then it's fairly easy, to protonate that, if I told that your analyte, right? So depending on the nature of the analyte, you can protonate it. So protonation happens where you transfer the proton from the reagent gas here, to the molecule, and now you've got, molecule that is actually already ionized. So other than proton transfer, you can also get what you refer to as hydride transfer. Now assume I've got a molecule such as that, which is a carboxylic acid, something like butyric acid and so on. Very, very common types of molecules, that has got carboxylic acid group. Now, we know this type of analytes can easily get deprotonated. You can easily lose these hydrogen, for them to acquire a negative charge. So similarly, this type of reagent gas, adduct, that came from the reagent gas, can react with the molecule, with the analyte, possibly that has a carboxylic acid, deprotonation happens, and then you lose that proton, and such that, you are left, with something that looks like that, again, that is ionized. So you can see, the different, mechanisms by which, protonation would happen, in chemical ionization. But the key is you're using a reagent gas, it gets ionized, and the reagent gas transfers the charge to the molecule, either by protonation, depending on the nature of the analyte, or deprotonation. As I said, it's a fairly softer technique compared to the EI. Now, the other ionization method, is a so-called field ionization method. Again, very, very simple in terms of its mechanism. You just have two electrodes. You've got an anode, and a cathode. You got an anode, and a cathode. And essentially in the anode, you're applying a fairly high voltage, environment. So essentially, the electrode, provides that electric field, to this environment. Very, very, very high electric field. Typically, as you can see, it's 10 to 20, kilovolts, of potential, that you're applying, on that anode. And so as your sample goes through the inlet, it is perturbed, by this very high voltage, environment, and that causes, ionization. It's not any different actually, than a power line, so it's really a power line. Anytime you've got, a power line, then the environment around the power line is actually charged. And I think all of us know that. Anytime you see a power line around, the environment around that power line is actually charged. In fact, if you walk close to a power line, you can feel it, in your body, sort of, the static charge, that you actually get because you are getting ionized, by the power line. So it's not very different, from what is happening in this case. So the analyte, gets through this power line, it gets charged, and then now it can be pulled, to the mass spec, using an electrode. And of course, the electrode in this case would be, for example, a negatively charged electrode that's gonna pull the positively charged ions, to the mass spectrometer. So again, very, very simple. And again, you can see the importance, of electrodes, in mass spectroscopy as far as, channeling, the electrons as well as the ions, to the detector. Very quick comparison here, in terms of mass spectra. Look at the mass spectra of EI, for that molecule, all right? Now, you can see the fragmentation pattern is fairly severe. In fact, take a look at this. The molecular weight on the molecular ion peak is absent. Why? Because of what I said, it's a very harsh technique. It tends to fragment, the ions extensively. Now, look at the chemical ionization spectra. Again, you can see it's not as busy, compared to the EI. Now, look at this, the M, or rather you've got the ion being M plus hydrogen, meaning it's protonation that has taken place. Why? Because you've got, an amine group here, and amines, of course, they've got lone pair of electrons, And the lone pair of electrons, make them fairly easy, for them to grab, a proton, from a reagent gas adduct, like I've already explained in the previous slide. So you can see protonation, is a method, by which ionization is taking place. But the key is, you can see it's not a very busy spectra, meaning it's a softer ionization method compared to the EI. Now, on the other hand, look at the field ionization, mass spectra. You can see it's very, very soft. You don't get fragmentation at all. So in terms of, the relative softness, you can see the Fi is a lot softer compared to the Ci. And of course, Ci is much softer compared to the EI. So let's now talk very quickly about these other methods, called desorption methods. And desorption methods, by their very nature, they are very soft, okay? And also they are very new. These are techniques that were only discovered, around, 1990s, 1990s, thereabout. So they're very new techniques. So moldy, a very simple technique. As I say, this is what my focus on in my PhD. Typically, you've got, a sample stage. And the sample stage actually is just basically a stainless steel plate, all right? So the stainless steel plate, you put your sample, and then you mix the sample, with what you refer to as a matrix. So you take the analyte solution, and then you mix it together, with what you refer to as a matrix. And the matrix, typically is an aromatic small molecule, that can absorb the energy from the laser. So you put, the analyte plus the matrix onto the sample stage. You dry it. After you dry it, you shine a laser beam, onto that sample. And when the laser hits, the sample, it gets ablated. All right? So the sample gets ablated, and at the same time, it gets ionized as well. Now, the ionization method in this case, actually, the mechanisms are not very well understood, but there are a couple of hypotheses out there, and most of the hypothesis is, depending on the analyte, the matrix sort of transfers the energy, after it's ionized, to the analyte. So in this case, it's very similar to chemical ionization. So the matrix, gets ionized. And then the matrix ion, transfers the energy, to the analyte, either again through protonation or deprotonation, or sometimes cationization as well. But I hope you can see, how straightforward it is. So the laser beam hits the crystal, and the crystal comprises the analyte mixed with the matrix. And the matrix gets, ionized, because it's actually added, in a higher volume, compared to the analyte, making it more probabilistic, likely that it's gonna capture the energy from the laser beam and transfer it to the analyte. And now the analyte, is accelerated, to the mass analyzer. In almost all cases, the mass analyzer for the moldy is actually the time of flight. So you're gonna find, that instrument, out there called the moldy TOF, MS, because TOF is sort of, the predominant actually mass analyzer that is used, with the moldy. Now, there are many types of moldy matrices out there, but you're gonna see in almost all cases, they are fairly small molecules, that are aromatic in nature, meaning, they can actually absorb, the UV visible radiation, that is coming, from the laser beam. And because of that, they transfer that energy, softly, to the analyte. I hope it's fairly clear. Now you choose the matrix, based on the analyte. And again, It's sort of a more of an experiment or trial and error kind of thing, where these types of matrices, such as ferulic acid, synapinic acid, caffeic acid, and so on, tends to be very good for polar types of polymers. In fact, you can see MALDI is typically used for big molecules. It's used for big molecules. And in fact, that's why the TOF, is typically sort of the conventional mass analyzer you use, because the TOF is typically used, for fairly big molecules. So you can see, these types of matrices are what are used, with sort of polar compound, with polar compounds such as proteins. Whereas, if you're analyzing, non-polar, polymers, such as polyethylene and so on, typically you do not use this type of matrices. You use matrices, such as dithranol, and so on. So there are many matrices out there. In fact, there's been a lot of research, and I did a lot of that myself, on how you select an appropriate matrix, because right now it's not very clear, how you select an appropriate matrix other than through experimentation. Now, the other type of technique that is very common, as I said before, is sort of the gold standard now, is electrospray ionization. Now, electrospray ionization, was developed by these two guys, John Fenn mainly, actually, who won a Nobel Prize, actually, for developing ESI in 2002. That explains, the importance of this technique, because it's totally revolutionized, the idea of protein analysis, or what people call proteomics, which is a big, I guess, field of study out there. And of course, it also revolutionized what you call the genomics as well. Of course, the genes, the proteins are what are expressed, by the genes. So it's sort of a connected field there. And because previously it was very difficult to analyze proteins, without digesting them with an enzyme. But what Koichi did is he developed a technique that is able to analyze intact proteins, without necessarily needing to take them through a sample preparation step of enzymatic digestion, so that you can make the molecule smaller. So for that reason, he was recognized for his work. And on the other hand, Koichi Tanaka, actually is a guy who developed the MALDI, and equally, he won a Nobel Prize, because MALDI is a complementary technique. Equally, as I said in the previous slide, you can see for the analysis of big molecules such as proteins, which were difficult before to analyze, without digesting them. So very quickly, how does it work? It's a very simple technique, and we play a lot with it, in the lab all the time. All what you have is a needle, very similar to the needles that you guys were using for your research project. The only difference is you apply a voltage, a high voltage on that needle. So you infuse your sample through that needle, and then you apply a very high voltage, typically plus 5,000 volts, or negative 5,000 volts, but very high voltage. When that happens, now you would find, the solution, that actually comes through the needle. And of course, the needle is a very small tip, typically 20 micron, thereabout. So the spray that you actually get, from that needle is actually charged, because of course you're putting, the sample, through a very high electric field environment. And so you get this jet, and this jet of a sample, is actually charged. Now, because the sample is charged, as it is, going across, it starts to repel each other, because of course you've got, lots of charges in it. This is a droplet. And of course, because these analytes are charged, they start to repel each other. And as it's repelling each other, it goes through what you refer to as a Coulombic explosion. So it goes through a series, of Coulombic explosions. And Coulombic explosions just means, you got these charged droplets, as they keep repelling each other, they break apart, into smaller droplets. More Coulombic, repulsion occurs, and then you get these series, of explosions, meaning in the end, you get a very, very fine mist, after a series, of these repulsive, Coulombic explosions. And of course, the reason they are happening is because, that you've got charged species of similar charges, that are repelling each other. And then after that, of course, it ends up, into the mass spec, okay? So it's fairly clear, fairly simple technique. Typically, you also infuse in, a little bit of nitrogen into this environment so that you can improve, the dissolution, so that you can remove most of the solvent. Because of course, the mass spec, you don't want solvent into the mass spec. You want dissolution, to be taking place as ionization, is happening at the same time. Again, a fairly simple technique, that is used for analysis of big molecules, such as this protein, angiotensin, but also, for small polar compounds as well. Now, another huge advantage of ESI, very huge advantage, is the fact that, you can form multiple charges as well. Multiple charges, okay? Remember, you are trying to analyze M to Z, okay? That's charge, that is the mass. As the charge increases, you would see the mass to charge, decreases. And that's a good thing, because you're able then, to do good resolution, of even very big, molecules, because the charge increases, and so the mass to charge sort of decreases. And so you can actually use different types of mass analyzers out there that are often limited, if at all you've got a very high mass to charge kind of species. So a huge advantage, of ESI is that it tends to form multiple charges. And again, that means you get a lot of information, from your data. And that's very, very common, of course, with proteins, because proteins have got a lot of amino groups, amino acid groups. And of course, amino acids, they've got the amide groups. And the amide groups can very easily be protonated, meaning you can have lots of protonations, and so lots of charges at the same time, meaning the mass to charge, becomes, fairly small, and that information becomes fairly useful. So very quickly, the other types of variations, of desorption techniques. There are many types of variations out there of desorption techniques, such as this thing, that is called the DART. Now, remember, these techniques were being developed, after September 11th, all right? And so the issue of homeland security, became such a big deal. And people thought, ESI or mass spec, is such a versatile technique. And also remember, the ESI, is happening without a vacuum. So you're doing ionization, in an atmospheric pressure environment, meaning, you can use it, sort of, easily in the environment, without needing a vacuum. And so because of that, people thought, they can actually develop the technique, for airport, security as well, especially, to sniff, things like, things like drugs, to sniff possibly things like, bioterrorist agents and so on. And so people developed or customized or adapted, these other desorption ionization methods, the ESI, to make them adaptable, for homeland security, especially, to use them in airports as well, which is actually now becoming a commonplace. You go to an airport, chances are there's a mass spectrometer there, based on this desorption technique. So in around 2005, somebody developed, this thing called DAT, which is direct analysis in real time. And look at this, very, very simple technique. All what it is helium gas, that is going through a needle electrode. Of course, anytime you see a needle electrode, just means it's just a wire that has got a high voltage on it. All right. And that helium, goes through that high voltage and it gets ionized and excited, of course, at the same time. It's a high energetic environment. Now, so you can think of it really as a reagent gas, this helium. Now, if you shine that helium, if you spray that excited helium, possibly, onto somebody's clothing. In fact, this is data, that came from that guy's paper that I showed in the previous slide. So he just spray, the helium gas on somebody's necktie and then channel those ions, to the mass spectrometer. This is the mass spectra, that he would generate. And based on that, you can tell, if, this person, is carrying, something like an explosive or something like that. If at all I see a lot of nitrates-based compounds, then possibly, there is a bomb, that is possibly present. And so again, you can see how people developed, these very simple desorption technique, where you take helium, you ionize it, using an electrode, sort of almost like field ionization, and then, you do you spray sort of that gas, onto somebody's specimen, the one that you're trying to analyze, and then you've got the mass spec, where the ions got to the mass spec and they get analyzed. Other types of similar techniques, that different people, have tried to make is what you refer to as the low temperature plasma probe. Again, you can see the relationship with the ICP. The only difference in this case is low temperature, meaning you wouldn't break down, you won't atomize, the sample. As you can see in this case, this is a discharge gas, that goes again, through a high voltage needle, and then that and then that gas, can be sprayed onto the sample. The sample can be somebody's textile clothing, it can be somebody's, suitcase, and then of course, the ions, you get the reagent gas that is ionized reacting with the analyte to transfer that charge to the analyte, and then you got the analyte, being sucked in to the mass spectrometer, for analysis, and then you can tell, what type of specimens or chemical entities are present, whether it's an explosive or even a drug, an illicit drug, and so on. So it's been used a lot, in airports and so on for that. But you can see again, it's understanding the mechanism, and then you can adapt it and innovate and create, different types of technologies. Again, so you can see in this case, it's just data, that I got from this paper to show you the low temperature plasma probe. And look at it. You can see the mass spec is very, very clean, meaning it's a very soft ionization method. Meaning, of course, that it's very easy to interpret, the data. That's what you want, especially in an airport environment. You want it to be very, very clear, so that the data doesn't need a sophisticated expert, to actually analyze it. So there are huge applications out there, of mass spectrometry. So not just the airport security, environmental analytics, the Mars, so-called Mars rover, it had exploring the Mars. They had a mass spectrometer, in that vehicle. And so mass spectrometry really is the gold forensic analysis, the gold standard now for lots of different types of applications. Food analysis, medical diagnostics, homeland security, and so on. Again, that's all that I'm gonna say about it, and hopefully, from what we have covered, it gives you a gist, of some of the aspects of mass spectroscopy and its scope of application.